Let's keep working on this exercise to find the unit normal vector. Alright, so far we have found the tangential and we found the derivative of the tangential because we need that and its magnitude to find the unit normal vector. Well, that's the first part. The derivative of the tangential. Now we need to find the magnitude of this madness here, which is actually a madness. So that's the magnitude of the tangential. That's the square root of negative t 1 plus t squared to the 3 halves quantity squared plus negative 1 plus t squared to the 3 halves squared. Okay, so number 1, negative t quantity squared becomes t squared, and 3 halves raised to the second power becomes, becomes a 3 only, right? So that's 1 plus t squared to the third, and then plus negative 1 squared, that's only 1, and the same in the denominator, 1 plus t squared to the third power. Alright? The good news here, we have a common denominator, so we can just combine these two together. So keep the denominator and just add t squared plus 1 to the 3 halves. And we can further simplify this because even though these two terms are not in the same order, they are both adding, and well, for addition, these are commutative, and essentially this t squared plus 1 is the same as saying t squared plus 1 to the first power, or 2 halves. So we can subtract 2 halves minus 3 halves. How many halves is that?
Yes, sir. There should be 3 in the denominator.
In the denominator, yes, that is true. Then let's forget about the fractions. No more fractions. That's yes. I was still excited with the fraction, but yeah. So yes, 1 minus 3. That's 1 plus t squared squared. And this is good because this is just 1 over 1 plus t squared. Alright? Now we can finally calculate or find an expression for the normal vector. Okay, so this will be n of t equals the derivative of the tangential divided by its magnitude. Alright, and well, let's write down the derivative of the tangential, which is this expression right here, negative t over 1 plus t squared to the 3 halves, comma, negative 1 plus t squared to the 3 halves, and the whole thing divided by this quantity right here, which is 1 over 1 plus t squared. So let's divide each component by this quantity, that is negative t over 1 plus t squared to the 3 halves over 1 plus t squared, comma, negative 1 over 1 plus t squared to the 3 halves over 1 plus t squared. Well, of course, let's divide the fractions by multiplying by the reciprocals of the fractions in the denominator. So I'm going to keep it here. So this should be, well, I have an extra page on my PDF file, but you can do this on the back side of your page. That's why I had to add another page. All right. So well, so this is the same as saying negative t over 1 plus t squared to the 3 halves times 1 plus t squared over 1 and raised to the 1 to the first power. I'm doing that for a reason. Number one, so you can see which one is numerator, which one is denominator, and because we're going to use laws of exponents to simplify this. And comma negative 1 over 1 plus t squared to the 3 halves also times 1 plus t squared to the first over 1. Let's simplify this using laws of exponents. So what is 1 minus 3 halves? Isn't it negative 1 half? So this will be negative t 1 plus. Oh yes, sure. This part?
Yeah, I write really
slow. And 1 plus t squared to the 3 halves. And wait a minute, no, that's to the negative 1 half. We say it, right? Negative 1 half. And comma negative 1 plus t squared to the negative 1 half as well. But of course we don't like negative rational exponents. Let's write this using positive rational exponents and change those to radicals. How about that? So that's negative t over the square root of 1 plus t squared, comma, negative 1 over the square root of 1 plus t squared. And that's the vector valued function that for every value of t, you will get a normal unit vector. And that's actually the second part of the problem. We're almost there. Yeah, it's just a plug in the value. So now that's n, which is this expression, evaluated at 1. Check this out. So that's 1 over the square root of 1 plus 1 squared, comma, negative 1 over square root of 1 plus 1 squared. Okay, what is 1 plus 1 squared in the denominator inside the radical? Isn't it negative 1 over root of 2? Okay, so that's the vector at n equals to 1. Now let's check the connection. This is supposed to be a unit normal vector, all right? But I mean, we really don't have to find the magnitude of this vector. I mean, if you want to find the magnitude to verify that, that's fine. But do you recognize these two values? Aren't they values in the unit circle? Yes. Right? In the unit circle, that's, I think, it's boom boom, yeah, that's 5 pi over 4. And well, since this is a unit circle, and if this is a vector, what's the magnitude of this vector since it's a unit vector? 1, right? So that's a unit normal vector. And well, this is the end of the exercise only, all right? Now, so I'm going to be honest. These exercises are not going to be as bad as this. But I chose one like this in particular. Well, number one, to refresh all our algebra. The homework may give you something similar, so you're prepared for the homework. If you get anything this crazy, like you go the second step and you go like, wait, is it this hard? No, yes. So these get this crazy. I mean, unless you get something like the trigonometric ones, for which we get cosine squared plus sine squared, those reduce really nicely to the Pythagorean identity equals to 1, you know. But in some cases like this, you know, and check the vector valued function, it was just something pretty that looked very innocent here, right? Just 2t and a t squared, nothing crazy. All right. What's the next topic over here? Well, number one, is there a shortcut to this? Well, yes and no. I mean, the yes, it's because this shortcut only works for vector valued functions into dimension for a 3D system, it's not going to work. But now the thing is, so we need to find another vector. So we find the tangential, and we need to find the normal vector, because we know that the normal vector and the tangent vector are actually orthogonal to one another. Well, the dot product between these two vectors has to be 0. And well, finding the tangential, well, it doesn't take too long as far as just getting the tangential. If we have to find the normal vector, well, that's where it gets a bit tough. However, well, how do we find that vector that becomes orthogonal so we can just multiply by that and get that vector? For example, number 1, think of the following. If we have some vector, whatever vector, A with B, what should we multiply this with so we get 0? So one vector times a vector of which form equals to 0? There's two possibilities to this, actually. And the number 1 possibility is
it negative B, negative A?
Negative B and A in this case, right? Because we want to make this add up to 0. The other possibility is B comma negative A, because A times negative B, that's negative AB, plus B times A, which is AB, that equals to 0. All right. The other possibility is to, well, get B, A times B, that's AB, and then minus B times negative A, which is AB, and this is also 0. Well, in other words, multiplying a vector by the same vector, but actually reversing the components, interchanging the components, and changing the sign of one of the components. All right, that's the trick to avoid all this problem. And we're going to verify. I'm going to verify it over here. So to get the normal vector without going through this painful process of finding the normal. The tangential, well, that was fine. A couple of quotient rules here and there. But I mean, the normal, that's the one that drove us the nuts over here. So in this case, one of the possibilities is get the tangential, multiplying by the normal by interchanging the components, changing the sign of the second component, or changing the sign of the first component. Well, let's verify this. Let's verify this with the previous example. So number 1. Again, we need to find the derivative. So, well, actually, I'm just going to use the information. That's the derivative. Well, the vector valued function is 2t, and yes, there was a typo. Here I have this negative t squared. Right, so it was a typo in the original problem. And, well, we got this to be the derivative, that's r prime of t equals 2 minus 2t. And then we also got that the tangential, just the tangential, not the derivative, is 1 over the square root of 1 plus t squared, comma, negative t over the square root of 1 plus t squared. And then what we're going to do in this case, I'm going to find the tangent vector at 1. Instead of going all the way through the normal vector, which is what we just did, I'm going to do the calculation in using the tangent vector. So in this case, this will be 1 over the square root of 1 plus 1 squared, comma, negative 1 over the square root of 1 plus 1 squared. All right. And, well, what are we going to get? The tangential, or the tangent vector at 1 for this vector valued function, that's 1 over the square root of 2, comma, negative 1 over the square root of 2. Okay? Now, for the normal vector, Again, without going through the painful process, there's two possibilities. Number one, negative 1 over root of 2, comma negative 1 over root of 1 over root of 2. That is interchanging the components and changing the sign. In this case, I'm changing the sign of the second component. What am I doing here? I'm sending the y component to become the x with its sign, and I'm sending the first component to be the second component, but changing the sign. Okay? That's one possibility. Or the other possibility is to 1 over root of 2, 1 over root of 2. Both positive. Now, which one is the correct possibility? It's going to be one or the other. Well, in this case, we need to see the direction of the curve. Because check the first vector. The first vector, it's actually going in the direction negative x and negative y, while the second possibility is going up or right and up. So those are two totally different directions, even though they're the same components. And to verify this, let's go to our graphing calculator in parametric mode. Okay, so alright, so we are in parametric mode right here, 2t and negative t squared. Okay, so when graphing this parametric function, make sure not to blink, because you may miss the direction in which this graph is being drawn. So let's see, graph. Oh, I was barely able to see this. Okay, so if you don't want the graph to go too fast, go to window, and the t step, well, it's of the order 0.1. Let me put something like 0.01. Okay, that was better, but still a little bit fast. How about, okay, 0.001. So when I'm changing the step, what the graph is doing is plotting points to the accuracy of 1, 2, 3, of 10 to the negative 3. That's why it takes longer to graph. Okay, so graph. Oh, it's now it's in slow motion, right? It's in slower motion, and we were able to see that it's going in this direction. This is what matters, not the shape. No, we're not looking at the shape, we're looking at the direction, because it could have gone in this direction. All right, so let's go back to the paper. So we have this graph, and it's going in this direction. And well, we should have a tangent vector, in this direction. Which one should be the normal vector, outside or inside? So in the concave side, right? So, and well, that's negative. Which one is it? The first one, right? This one is the good one, not that one. And well, for the last topic for this section, it's, what do we have? The tangential and the normal components of acceleration. And I'll see that in a minute. So well, what's the theorem? What's the definition? R is in the position is a position vector for a smooth curves, and and n exists. Well, the fact that n exists is because t exists, of course. Okay. And also, the acceleration vector lies in the plane determined by the tangential vector and the normal unit vector. So, well, another way to say this is that the part of the accelerations acts in line in motion on both the tangential and the normal vector. Well, without reading the whole paragraph, let's see this in the picture. So, Let's forget about the normal and the tangential. Let's focus on this acceleration vector. So you might remember from when we covered acceleration and velocity vectors, we said that the velocity vector, which gives us the tangent vectors, go in the direction of motion. In this case, let's assume it's going in this direction. All right, just so it makes sense. And the acceleration vectors go in the concave side of the curve along the direction. So, in other words, this is what we're doing. You might remember from, I think this was day 1 of class, when we added two vectors. So suppose we add the tangential with the normal using the parallelogram method. All right? So what we're doing in this case, we are decomposing this acceleration vector into two components, the normal component and the tangential component. In other words, this AT that we are going to find here is the projection of the acceleration vector onto the tangential and the projection of the acceleration vector onto the normal component. And because, well, think of this vector going forever, right? We don't know what this is. And let's see, this is blue. This one goes on forever. But, well, in this case, we just care about the projection of this vector, about the length of this vector. That's going to be the normal component, and this would be the tangential component. In other words, what we're going to do is break up the acceleration vector and write it as a linear combination of the tangential and the normal vector, which is this expression right here. So that is some number times the tangential plus some number times the normal equals the acceleration vector, where the acceleration component of the tangential component of the acceleration is the acceleration times the tangential, and the normal component a sub n is the acceleration vector times the normal vector. And, well, you've seen the painful process to go through the tangential and the normal vector. So lucky for us, we have alternative formulas. And actually, I gave you another handout right here. This other handout, which is 2 pages, it's actually to replace the last page of the handout I gave you before, because I didn't put these formulas on the older one. And for the 2 exercises, I added more space to it, because more space means more fun, right? And with the space I gave you before, it was not going to be fun, so it's not enough space. All right, so let's find the components of the acceleration on the circular trajectory 2 cosine 3t, 2 sine 3t. And, well, number 1, let's describe this trajectory. Well, this is a circle of radius 2, right? That's the coefficient of cosine and sine. And let's see. So looking at the formula, I didn't update my PDF file. Okay. Well, I'm going to need one of these. I was supposed to put a new one here. So, and this first exercise, we're going to do it using the second alternative. The a sub n equals the magnitude of the cross product between the velocity and acceleration over the magnitude of the velocity. All right? So find the components of the acceleration on the circular trajectory given by this equation. Well, so number 1, we need to find the velocity vector. That is v of t equals, that's going to be using a mini chain rule. The derivative of cosine is negative sine of 3t times 3 times 2. That's a negative 6 sine 3t. And that's going to be 6 cosine 3t. Okay? And well, to find the accelerate the form, I mean the component, the normal component of the acceleration, we need to find the magnitude of this velocity vector. So let's go ahead and find it. So that's going to be negative 6 sine 3t, quantity squared, plus 6 cosine 3t. So that's going to be the square root of 36. Well, the GCF is going to be 36. Well, that's a sine squared 3t plus 36 cosine squared 3t. And that's the square root of 36. Factor out 36, we get sine squared plus cosine squared, isn't it 1? And that's the square root of 36, which is 6. So that's the magnitude of the velocity vector. Okay. And well, we need the magnitude of the velocity vector to find two things. Number one, tangential, and that's also part of the normal component of the acceleration. Okay, so number one, let's find the tangential. The tangential t of t equals r prime of t, or the velocity vector divided by its magnitude. So in this case, this will be the velocity vector, which is negative 6 sine 3t, 6 cosine 3t, divided by the magnitude, which is 6. And in this case, well, this one is easily reducible, so we can reduce this very easily. That's just negative sine 3t, comma, cosine 3t. Okay. Well, what else do we need to find the normal? So we got the tangential, we got the first part. So we need to find the acceleration component. So we got this part, we need to find this, we need to find these other three. Okay, so what else do we need? We need the acceleration vector, right? I didn't find the second derivative, so that's the acceleration, and that's going to be is that a negative 18 cosine 3t, comma, negative 18 sine 3t. Okay, and well, we have all we need to get the tangential component of the acceleration. So that's the first term in, well, let me have everything till the end instead. So now we need the cross product between the velocity and the acceleration vector. So let's go ahead and set it up as well. So velocity cross with acceleration, that's I, J, K. But wait a minute, we have a 2D system here. All we're going to do is make the third component equal to 0. Okay? So, I'm going to need more space for this. So for I, so that's the velocity vector, which is negative 6 sine 3t, J, which is 6 cosine 3t, and K, 0, and the acceleration vector, which we have just above, negative 18 cosine 3t, negative 18 sine 3t, 0. So we need to find the cross product between these two vectors. Well, I'm going to show the calculation. I'm not going to do like in the previous sections, in which after a while I just gave you the result, especially because we didn't have vectors with variables looking like this, and we didn't do the cross product with this kind of vectors. I'm going to show the whole thing here. So that's I. Let me repeat the first two columns. So that's negative 6 sine 3t, 6 cosine 3t, negative 18 cosine 3t, negative 18 sine 3t. Okay. All right. So let's multiply the main diagonals. I'm going to do one at a time. So that's I times 6 cosine 3t times 0. Well, I don't have to write anything for this. J times 0 times negative. Well, I don't have to write anything for this because that's a 0. But over here, K times 6 sine 3t times negative 18 sine 3t. That's going to give us 18 times 6. What is that? 108. 108 sine squared 3t. All right. And then let's do minus the multiplication along the secondary diagonals. That's the ones for which we multiply backwards. That's j times 6 sine 3t times 0. Well, that's going to give us a 0. The second calculation, that's it's I times 0 times negative 18 sine 3t. That's going to give us a 0. And k times 6 cosine times 18 cosine. Well, that's another, but in fact it's a negative 108 cosine squared 3t, which reduces to how about factor out 108 and multiply by sine squared 3t. Oh, I forgot to say that this is in the direction of k, right? K and k, okay? And that's sine squared 3t plus cosine squared 3t in the direction of k. And well, again, we have the Pythagorean identity, which will reduce this significantly. That's equal to 1 times 108. That's 108 in the direction of k. And writing this in component form instead, that's a 0, 0, 108. Up to this point, so far so good? Well, we also need the magnitude of this vector. So that is the square root of 0 squared plus 0 squared plus 108 squared. But don't need to square the 108 because that's plus 0, and then the square root of 108 squared, it's going to be 108. All right. So let's see what we have so far. So, oh yes, I didn't update my file. I wish I did it. Anyway, I'm going to do it for the next example. So far, well, actually we have everything to number 1. The tangential component of the acceleration, which is the dot product between the acceleration vector and the tangential vector. Let's write them down one at a time. So the acceleration vector, which is negative 18 cosine 3t, negative 18 sine 3t, dotted with t, the tangential, which is right here. The tangential is this vector right here, sine 3t cosine 3t. And when we find the dot product between these two vectors, this is 18 cosine 3t, that's negative 18 cosine 3t times sine 3t, and in this case plus, and actually it's going to be negative, minus 18 sine 3t times cosine 3t, which is in this case 0. Yes?
The value of t sign should be negative.
Which one?
The second one?
Yeah.
This one?
Yeah, that one should be negative.
Oh, yes. This one's a negative. Oh, yes, and that turns into positive, and yes, that's what makes it a 0. Thank you. So that's the tangential component of the acceleration. Well, I'm going to use the blank space for the next exercise. You have the whole page on your handout. So for number 2, the normal component of the acceleration here will be, where's my calculation here? Oh. The normal component is the magnitude of the cross product between the velocity vector and the acceleration vector divided by the magnitude of the velocity vector. And well, those are quantities that we already computed above. Let's go back to, the magnitude of the cross product, isn't it 108? Divided by the magnitude of the velocity vector. What did we get for the magnitude? 6, right? Which reduces to 18. All right. So what's the picture? So let me just draw. Oh, it's a circle. It's circular motion, so it's going to be easier to describe. So it's a circle, radius 2. All right, it's a circle of radius 2, and well, so at any point, in this case, it's not specifying at which point, and it can be at any point because curvature, it's the same at any point, and this frame, this normal and tangential will have the same orientation at any point. Like for example, over here, tangential, normal. Tangential, normal, they will have the same shape, so it's not going to change really. So what we're saying here is that the tangent, normal, and some acceleration vector right here, it's broken up into these components. That is, the magnitude on the tangential is 0 units. Actually, it only moves along the acceleration in this case. Okay, in this case is some 18 units, so to speak. So that's the picture of how this acceleration is broken up into the normal direction and the tangential direction. All right.